Phenomena. Do.
Again, she started that in my head again.
Stoichiometry. Isn't it awesome?
You remember this from last class?
Yeah, we got a balanced equation. And we're trying to predict amounts. Guys, we're going to be doing more difficult problems now. A little bit trickier. These are the ones that require, well, it's going to require you to write smaller, I think, so we can get it all on the screen. So it's important that we're now not going to just say from moles to moles, but we're going to do a different problem. So let's say that we've got 16.2 grams of hydrogen. So kind of a weird number, right? And I want to know how many grams of water would be produced. Now let me give you a hint. When I'm doing these problems, I think it's important to label what you know and what you don't know and put it in the equation. So when I have a problem like this, it's going to be written out in words, and we've simplified it a little bit here. I will write this, 16.2 grams underneath the hydrogen, and I'll put question mark grams underneath the water. And that frames the question and tells me what I have, my given, if you will, 16.2 grams, and what I'm trying to find, the water.
So we have this table that you're looking at right now, and
so now, on the mole map, or the land of the mole, if you're looking at the land of the mole, we're trying to go from grams to grams, and what you'll notice is there's different fractions along the way. So always start with what you know as a fraction over 1. So you can see Mr. Dimitrich, 16.2 grams. Notice he wrote H2 over 1. Now, if we go back to the land of mole, to get there, we have to go from, now let's just big picture, we have to go from grams of A, if you will, to moles of A, moles of A to moles of B, and then moles of B to grams of B. If you see this, we're going to have a bunch of different fractions.
Let me jump in here just for a second, because if you take a look at this, prior to this, didn't we say the equation is written in moles?
Yes.
So we did a bunch of this, like if I know the moles of H2, because there's 2 moles of this for every 1 mole of this, we can do that really easily. If you give them grams, this equation isn't in grams, so we have to convert it to moles.
Yeah, because you can't say this is 16.2 and this is 16.2 because it's 2 and 2, because their grams are not the same. So we have to convert to grams. We've done this before, so we look up on our periodic table and we find that hydrogen has a mass of 1, so it's 2 grams for every 1 mole.
Now why did I put this grams on the bottom?
Because you need the grams to cancel, and you were actually super accurate with 2.016. That's fine. Roughly 2 grams for every 1 mole, all right? And what can cancel now?
Grams cancel.
Now let's go back to the land of the mole, and you notice where we're at now, and we need to get from moles to moles. So we have a new fraction that we need to make. And to get from moles to moles, we need to get the moles down here. So notice that the moles are on the top, moles of H2. So Mr. Dimitri's going to write moles of H2. In fact, 2 moles of H2. Now, where did you get that 2 from?
Now, I know that you like putting it in there without putting the number in first, but the number is from the recipe. We know that there's 2 moles of H2 for every 2 moles of H2.
So this is the step where we use the recipe, right? It's the 2, in this case, 2 to 2. 2 moles of hydrogen, 2 moles of water. Now, I see something can cancel out. What can cancel out?
We go into canceling frenzy here of our moles of H2.
And we've got one more step, because now we want to get to grams of water. Now, again, looking back at our mole map, or the land of the mole, you see now we're going to go from moles of B to grams of B, and now we have to use the molar mass again. And the molar mass, of course, we find that from the periodic table. And 1 mole of water, and water is H, there's mass of 2, 16 for oxygen. Now, one thing you might have forgotten is if you've got a big set of fractions right here, here's the rule. Everything on top, you times. Everything on the bottom, you divide. Now, notice I've got 2 different numbers. You can ignore the ones because they're divided by 1, same thing. So listen how I type. I'm going to say 16.2 divided by, I'm going to cheat a little bit. Divided by 2, I'm not going to type 2.016. Times 2 divided by 2, times 2 divided by 2, times 18. And I get 145.8 grams of water. Now, I cheated a little bit and didn't do the exact number, 2. That's not that difficult, but you have to follow the land of the mole.
And you can stop anywhere along the way, right? So let's say I hadn't asked you to go from grams of this to grams of this. Let's say we changed this and we wanted to go to
just moles.
Let's go to moles, right?
Yeah, you would just skip this last step, right? Because if you're in the land of the mole, again, let's follow the pattern. You'd go from grams of A to moles of A, or to moles of A, moles of A to moles of B, done. All right, we have another example. It's a little bit different. We have a different reaction. This is potassium chlorate, and it's a really cool chemical, by the way, because when you heat it up, it turns into oxygen gas, which is super crazy flammable. This is a fun chemical.
Yeah.
But first of all, first thing we always do is we start with a what?
Balance.
Balanced chemical equation.
1K here, 1K here.
Happy.
1 Cl here, 1 Cl
Happy.
here. Oh no. 3 oxygens here.
Not happy.
2 oxygens here.
So
now, if you have 2 and 3,
6.
yeah. So why don't we multiply this by 2 and this by 3?
Yep.
Now, when you do that, though, doesn't it change the other variables in it
Yeah,
as
the
well?
KCL is going to have to be
2 Ks here. We only have 1 K here. If we put a 2, wouldn't that balance off?
Yeah,
from
that's
that?
awesome.
Before we go any farther here, it matters when we're dealing with gases that we know which things are gases, which aren't. So we're going to put this in here. This is a solid.
Yeah.
This is a
Solid.
and this is a
Gas.
gas, and that's going to become important in this particular problem.
So what we're going to do is we're going to do a problem that has mixed units. So let's say that I've got 10.2 grams of potassium chlorate, and I want to find the number of liters of oxygen gas that are formed. All right? So gases are strange. There's something that's really cool about gases, that if you have 1 mole of gas, it always takes up the exact same amount, 22.4 liters. By the way, that assumes that you're at room temperature, 25 Celsius, and you are at sea level. We'll learn later on what you deal with when you're at a different temperature or a higher altitude or lower altitude or whatever.
The code word is STP, what he just said, but again, don't worry about that.
And the fancy thing is that it's 22.4 liters in a mole, and this is like a fraction where you can flip it upside down. You'll see it's in the land of the mole, right? You see that. So I'm going to start with what I know is a fraction over 1, or Mr. D is 10.2 grams of KClO3 over 1.
Now, following what he did before, we're going to write this
Yes.
10.2 grams
Yeah,
underneath
there.
here, just so we know this is our starting point. Where's our final point? Where do we
I
write
want this and question mark, but I'm going to write a big L next to it because the big L indicates that I want so many liters of it.
And to follow this along here, just to keep track of it, I always like to put a little arrow to tell me where I'm going between the two.
That makes sense. Perfect. So first step, land of the mole, I need to go from grams to moles. Now this is a little trickier when I have to find the molar mass of KClO3. So I'm going to do that real fast. And I'm going to round to the nearest whole number. Potassium is 39 plus 35.5 for chlorine plus 16 times 3. I want to say it's 122.5. So that's the molar mass. Remember, we've done that before. Molar mass, 122.5. Just added up KClO3. That's grams of KClO3 to 1 mole of KClO3. Now, in the land of the mole, where are we at? We're at the moles. Now we're going to go from moles to moles. So why don't you write out the moles to moles without the numbers. So the moles of KClO3 is at the top, and we're going to put moles of KClO3 on the bottom, and I want to convert to moles of oxygen.
Well,
Now,
we forgot one thing here.
Yeah, you forgot the 1. Yeah.
Well, that is true, but we also forgot to cancel the grams.
Oh, yeah. And now, where do I get these numbers? This is from the recipe, if you will, the chemical reaction. So it's a 2 and a 3, or a 3 and a 2, which way is it? 2 on the bottom and a 3 on the top. Because the 3, this is this 3, and this 2 is that 2. But I don't want to know the moles. If I stop right now, I have moles of oxygen, but I want to convert to liters. Now we have this new fraction. Again, look at the land of the mole, and this is where we use the 22.4 liters of any gas, and we're working with a gas, oxygen gas. So what we just say 1 mole of oxygen gas on the bottom is equal to the big number that always is the same and never changes, 22.4 liters. And we can cancel, and on my calculator, this is what I'm going to type in, 10.2 divided by 122.5 times 3 divided by 2 times 22.4. I get a grand total of 2.79, and that will be liters of oxygen. And that's the answer. We're going to do one more example, and then we'll let you work on your own. All right, we've got one more example. We've got a chemical reaction on the board. It's actually a fancy reaction, a famous one called the Hubbard process. They make explosions out of stuff. It's really cool. Anyways, side notes. But it's not balanced, so we got to balance this. So we've got 2 N's, we got 1 N, so we can put a 2 there and fix it, I think. But that gives me what H's?
6 H's
6.
there. Only
So
2
I think we
here.
need a 3 there. So let's say we've got 15.7 grams of ammonia.
I'm going to put it here just because I don't want to write it out here.
Yeah. And now I want to know is how many molecules of hydrogen gas are formed.
Row.
Molecules. This is a little different one. So it's still land of mole. We're just going to use a different fraction. So we're going to start with what we know is a fraction over 1. We always do the same thing, right? We're going from there to there. By the way, notice that we're going backwards. It's okay. This is basically, I have 15.7 chocolate chip cookies. How many cups of flour do I need? That's really what we're doing, right? So if you have 15.7 grams of NH3 over 1, And I need to get my calculator. Nitrogen has a mass of 14.
17.03.
And hydrogen is 1, so it's 17, or in exact figures, 17.03. It's actually not exact.
Not my first rodeo, but yeah, it's close to this.
Grams cancel, right? Now we are at the next stage. The next stage is we need to go from moles to moles in our land of the moles. So it's moles to moles. So we'll write moles of NH3 because we want to get the NH3 to cancel. And moles of H2 on the bottom. Now where do we find the numbers? From the balanced chemical equation. 2 and 3. By the way, sometimes they're 1 and 1. It just depends on the reaction, right? And what can we cancel out? Back to the land of the mole. Now notice, now we have another fraction that we can use. What? That fraction is Avogadro's number. So we're just going to use Avogadro's numbers like we've done before. The 6.02 times 10 to the 23rd molecules are in 1 mole. Always the same. Always, always, always. So we put that in our fraction, right? But we got to decide which goes on top, which goes on the bottom. Well, molecules in moles, since the moles are on top, I'm going to put moles on the bottom.
Also keep in mind that you should be keeping the compound you're
Yes,
using.
you have to keep H2. Notice how Mr. Demetrius is very good about that. This is a lot of writing. And then there's the calculator thing. All right. Now, you got it? Okay, hold on. We've got a little cancellation. And yeah. And what are we left unit-wise with molecules of H2? Now, how do we do this in your calculator? Now, I haven't said this before. Follow along with your calculator. I'm going to type in 15.7. Next step is divided by 17.03 times 3 divided by 2 times 6.022. Now, careful, careful, careful. I do not say times 10. I push the double E button, 23. And I get the number 8.32 times 10 to the 23rd. And that will be molecules H2. By the way, I think it's okay to show you this. When I write, Mr. Demetrius, you write moles, and I typically just write MOL for the abbreviation for moles. And for molecules, I write the abbreviation MOLEC. I don't write the whole word out. So we can save you a little bit of writing. If we're doing a liter problem like the previous one, it's just capital L. I think that's pretty easy. Yeah.
Just a side note here, because we did learn significant figures for a reason. Whenever we're doing our final problem, you see we have 3 significant figures here, 4 here. Now these are exact numbers, so they don't count. And then we have 4 here. Whenever we're multiplying and dividing, don't we take the least number of significant figures?
And that's why I only gave him 8.3, because actually the calculator says 8.335455, a bunch of digits, and I, in my head, rounded that to 3 significant digits, knowing that we had 3 significant digits right here. By the way, if it could have rounded up possibly to 8.33 or something like that if the next digit was a little bit higher than a 5. Folks, you're only going to get better with this with practice. So, mana.
Let's practice.
Do.
We'll play it in class just so you remember what it is. This is how old people dance, by the
way. You saw me dancing at the assembly, and you know I suck at it.
Not gonna do it. Hey, see you guys next time.
I still feel bad about it. I still have issues that you didn't vote me in, by the way. Just FYI.
Super.
I should have beaten right away, just saying.
Well, that's always true, though.
Yes,
That's always true. Shakes fist at Braidaway.